Hello. Okay. Thanks for the opportunity to talk. So today I will be talking about joint work with Tianyi Yu over there about a bunch of polynomials. So at this moment, you can see there are 4 very big letters on this whiteboard. That will be, all the polynomials will be kind of look at them. So the first one, upper left, is the Schubert polynomial. So now we all learn about Schubert polynomial. And there are a couple more. So if we take the K-theoretic generalization, we will get the Grothendieck polynomial, which are the polynomial representatives of the K-theory of the flag varieties. So, and we will also be looking at 2 more polynomials, key polynomials and Lascaux's polynomial. I will talk about their connection, and I will complete the diagram in the end. So first, we'll look at the definition of Grothendieck polynomials. So we have learned from Anna's lecture last week that if we want to compute the Schubert polynomial for a permutation, we start from the long element, and we use this divided difference operator downward to compute the polynomial. And for Grothendieck, it's defined in an analogous way, except that we have this extra beta times xi plus 1 term in there, and you will see later that it will contribute more terms. But if you just think, if you substitute beta equals 0, we actually recover the divided difference operator. And we can take a look at the effect on the computation. So if we compute the Grothendieck for the permutation 4, 3, 2, 1, so this is a long permutation in S4. So it's just a staircase single monomial. And it equals the Schubert. If we want to compute something that's not the long element, we need to apply this beta divided difference operator several times. And I computed these 2 examples here. You can see that you will get actually an inhomogeneous polynomial. So now I want to ask you, where is the Schubert? The Schubert is the constant term of the Grothendieck polynomial. So you can connect the operator side with the polynomial side. That if you think beta equals 0, all the higher order term will vanish, and we're only left with the constant terms. So in the first parentheses I denoted, they are the Schubert polynomials. So we have beta divided difference operator here. All right. So we have just observed that the constant term of the Grothendieck polynomials are the Schubert polynomials. We can think they are the bottom layer of this inhomogeneous polynomial. So in the example right here, I have marked in red that that term, the bottom layer, is the Schubert polynomial for 2, 1, 4, 3. And now we want to ask the following question: what is the leading monomial for this Schubert polynomial? So before we talk about leading monomial, we need to give a monomial ordering. So this is actually the same ordering. I think in the morning we see the tail lexicographic order. So that is, we compare monomials by first comparing the powers of x and the last variable, then backwards. So in this scenario, x1, x2 cubed, x3 squared will be smaller than the one right here because it has x3 cubed there. So now we can talk about what is the leading monomial for Schubert. And the answer is Lemur code, work by Billy, Jakosh, and Stanley. So what is Lemur code? It is also known as the inversion code. So how do we find the inversion code of a permutation? It's very simple. So it is a permutation statistics where the i's position, you look for how many elements to the right in the one-line notation of your permutation is smaller than this one. So if we want to compute the Lemur code for 2, 1, 4, 3, and we look at the first entry is 2. How many elements to the right is smaller than 2? 1. Right, so the first entry of the inversion code is 1, and for 1, the second entry 1, there's nothing smaller than it, so we get 0, and we can complete this process, we'll get Lemur code 1, 0, 1, 0. I hope we're all good. And that answers the leading monomial question. That is saying the leading monomial is x1 times x3. And now we look back at this example at the top, you will see x1, x3 is indeed the leading one. Other two doesn't have x3 in it. Okay, so this is answered for the bottom layer. So now, when we solve the bottom layer, we want to think, how about the top layer? So the top layers of Grothendieck, so in this example I highlighted, it's x1 squared, x2, x3. It has a fancy name called Castelnuovo-Mumford polynomial. So what is the leading monomial for? So for the top layer of Grothendieck, so we use the notation hat to denote this is the top layer, the highest homogeneous component of this polynomial. And the answer is given by Jianping, Pan, and Wagon in terms of Raj code. So this is another permutation statistic. So what is this? So the Raj code of a permutation is again a sequence of integers. So if you want to compute the r's entry of the Raj code, you look at the sequence starting from r's position, and you try to construct a longest increasing subsequence containing that r's element. So if we want to compute the Raj code for 2, 1, 4, 3, so the first entry is 2. What is the longest increasing subsequence that starts with 2? We have 2, 4, or 2, 3. There are two choices, but they have the same length. So in the Raj code, we actually count the number of elements that's not in that longest increasing subsequence. So whether you pick 2, 4, or 2, 3, you're skipping 2 numbers. So that 2 will be the first entry in the Raj code. And then we can do the next entry for 1. What is longest increasing subsequence? For starting with 1, 1, 4, or 1, 3. Again, it's skipping 2 elements. And it's skipping 1 element, 1, 4, or 1, 3. And then when we move to the third entry, 4, it's already the largest element. So it will skip the last element, 3. So we get 0. 1, then 0. So this is the Raj code for this permutation. I hope it makes sense. So this is defined by Jianping, Pan, and Wagon. All right. So actually, moreover, in addition to computing the leading monomial of top Grothendieck, there is another result by them that 2 permutations sharing the same Raj code, if and only if their Castelnuovo-Mumford polynomials are scalar multiples of each other. So you can see that this leading monomial, it's a very strong determine the structure of this polynomial. Okay, so far the content has been purely in terms of a polynomial and some combinatorics. So now I want to add a touch of the summer school to explain a little bit what's the behind the Castelnuovo-Mumford polynomials, why it's important. So first, so this is related to Castelnuovo-Mumford regularity. So to explain this, we'll use the same setup as in Patricia's homework. So it's lecture 1, homework part 2. So S is a polynomial ring over the variables Zij, okay, and IW is the Schubert determinantal ideals for W. So recall what did we learn from Patricia? So this Schubert determinant ideal IW, if you quotient S by IW, we will get it is Cohen-Macaulay, and we will consider a minimal free resolution of this quotient of graded S modules. How do we do that? We follow Patricia's homework setup, and we do the causal complex computation, and we get. So let me explain using this example 2, 1, 4, 3. So that will be our rounding example today. So we have the permutation 2, 1, 4, 3. We compute essential set, which is Z11 and Z33. So, and this will give the Fulton generators. Do you still remember? So one is Z11. The other is the 3 by 3 upper left submatrix. Its determinant. So we'll call them P1 and P2. And because they are because they're cohomolcularly, we can, and the P1 and P2 are regular sequence, we can compute its minimal free resolution right here. I asked our TA and she actually said it's correct. Okay, so where is this Casanova amount for regularity? So you look at this free resolution we got, like each part, there's some maybe direct sum of something. We will consider the greatest thickness of this minimal resolution. What does that mean? So we will start from here saying this is the i's, the zeroth one, the first one, and the second one in the free resolution. And we'll use the shifted grading I to minus its position in the free resolution. So this is just 0. This 3 minus 1 gives us 2. 1 minus 1 gives us 0. And this 4 minus 2 gives us 2. So after we write down the thickness, the largest number you see is the Casanova-Mumford regularity. It measures how complicated your Schubert determinant ideal is. And so this is more like in the community algebra point of view, a work of Knudsen Miller, Rajagopal, Robichaud, Disler, and Wagon show that, well, we don't need to compute the free resolution. We just look at the difference in degree in top Grothendieck and Schubert. The increase in degree gives us the Casanova-Mumford regularity. So back to our rounding example 2143, the Schubert part has degree 2. And the top Grothendieck part has degree 4. So increase is by 2. I hope that makes sense. And if you haven't tried Patricia's homework, I highly recommend it. Okay, so that's so much for Grothendieck, and we know we have some understanding about this Casanova-Mumford regularity and why we care about finding the leading monomial so bad. So, okay, so now we are down here to our third polynomial, the key polynomial. So when we compute the Schubert polynomial using the divided difference operator, we'll drop the degree as we march in towards a smaller permutation. And there's we can have a degree preserving version, which is pi I, which I think is it here? Right. Pi I, before we apply the divided difference operator on this polynomial, if we multiply it by xi, we can preserve the the degree. So now let's look at the definition of key polynomial. So key polynomials, unlike Schubert and Grothendieck, they are labeled by weak compositions, say alpha. If your alpha is weakly decreasing, then it's just a single monomial. For example, weak composition 210 is weakly decreasing, so the key polynomial for it is just x1 squared x2. Now, say if you want to compute weak composition 120, because the first one is smaller than the second one, we need to apply this pi 1 operator. After you do the algebra, reduce them, you always get a polynomial. So in this case, we get x1 squared x2 plus x1 x2 squared. So the key polynomials are also known as the de Morgan character, are also called non-symmetric Schur functions. So how do you get the Schur polynomial from a key polynomial? Well, you just let alpha to be weakly increasing. Right, so this is the key polynomial. So now we have look at the three polynomials. So horizontally, we can do K-theoretic generalization. Vertically, we can do degree preserving. And if we do both K-theoretic and degree preserving, we get our fourth polynomial, Lascoux's polynomial. So similar to key polynomial, it is indexed by weak compositions. Again, if your alpha is weakly decreasing, it's just a single monomial, x to the alpha. If you want to compute Lascoux's of 1 to 0, you need to apply this pi I beta. pi I beta operator. So beta denotes the K-theoretic generalization, and pi denotes the degree-preserving version. And then you do the algebra, and you get a polynomial. Again, we see that we get a inhomogeneous polynomial. So we have degree 3 part and degree 4 part. So again, similar, whenever we do beta, like a K-theoretic generalization, we set the beta equals 0. We'll recover the before the K generalization. So if you think beta is 0, then it's just pi I. So we recover the key polynomial. You can also see it's the constant term. We'll see in a little bit. And furthermore, Lascoux's polynomials are closely related to Grothendieck polynomial. Despite at this point there isn't geometric or representation theoretic interpretation of Lascoux's polynomial, we do have the result that Grothendieck polynomial expands positively into Lascoux's polynomial. So this is a result of Shimozono and Yu. So again, we'll ask the same question. For this inhomogeneous polynomial, what are the leading monomial for the bottom and top components of Lascoux's polynomial? So in this example, I show you the Lascoux's polynomial for 0, 2, 0. So what is the leading monomial here for the bottom part? It's x2 squared. Yeah, that's great. So actually, can you see the answer in general? The answer is x to the alpha. Okay, it's very simple. So what about the top layers of Lascaux? So in this case, we can say, oh, it's just x1, x2 squared. So how can we compute them? The answer is snow diagrams. What is a snow diagram? Apparently, we expect some snows. So let me explain using this following example. Consider this weak composition 2, 0, 4, 3, 1. So first, what we're going to do is draw the key diagram for this weak composition. So this is very simple. You draw alpha I boxes in the ith row, all left justified. All right, and then we're going to work from the last row, row 5, and we'll look for the rightmost box in that row such that there is no dark cloud in that column. So this one is actually very simple. We have 4 pieces of dark clouds. And what will happen next when we have dark clouds? We will snow. Okay, so we have a bunch of snowflakes. So in this diagram, just be careful. So here in the second row, we actually have an empty position here. So there's not a dot or snowflake. So how does that compute the leading monomial for top Lascaux? Yes? Sorry? Right, so for each dark cloud, it will just snow. So in every unoccupied position, it will leave a piece of snowflake. Does that make sense? Yes. So now how do we find the leading monomial for top Lascaux? So we'll write down the weight of this diagram. So this is very simple. Just count how many cells are occupied by something in each row. So in row 1, there are 4 boxes. In row 2, we have 1, 2, 3 snowflakes. Just be careful, the middle box is empty. And then we have 4 things here, 3 things here, 1 thing in the 5th row. So this we call the Raj code on for weak composition. It's 4, 3, 4, 3, 1. All right. So once we get that, we show that the leading monomial for top Lascaux is just x to the Raj code of alpha. So in the previous example, the leading monomial for this particular Lascaux polynomial is this monomial. And we also show similar results that 2 weak compositions have the same Raj code if and only if their top Lascaux polynomials are scalar multiple of each other. Least, can you say least
common multiple of all the other monomials. Both of the ones you showed.
Yeah. a good question. Tianyi, do you know the answer on top of your head? Okay, ball is throwing. Okay, maybe my example are very coincidental, yes. Oh, yes, yes. So in row 1, there are 4 boxes. On row 2, there are 3 boxes because the second one position is empty. It just looks like there's box, but there's like we put dot for where, and so snowflake and dark clouds for where there is actually a box. So 4, 3, 4, 3, 1. Does that make sense? Okay. All right, and so now we know how to compute the leading monomial for top Lascoux, and our tool is node diagram. Now we think, oh, recall, how did we do that for Grothendieck? Oh, we compute the longest increasing subsequence, and then how many letters are not in it, right? So actually, we can do snow diagram for top Lascoux as well. So I'll explain through this example. So say take the permutation 3, 7, 2, 1, 5, 6, 4. Okay, in S7, we will compute its Ross diagram. Remember, Anna has taught us how to draw the Ross diagram, but warning, we are writing it upside down. We're going to start the first entry in the bottom. So 3, 7, 2, 1, 5, 6, 4. And then we're going to shoot a laser to kill all boxes for each mark. And we remove the mark, and we get the Ross diagram of this permutation. And we do the exact thing. We will draw dark clouds and let us know. So we will look for the topmost row, and we look for the rightmost box where there isn't already a dark cloud there. We put a dark cloud here, so there won't be a dark cloud here, right? Because there's already one. And there's a dark cloud here, and dark cloud here. So we have 1, 2, 3, 4 dark cloud, and they will snow. So these two they fail to snow because it's all occupied to the bottom. And this one snows 3 snowflakes. This one snows 1 snowflake. So, and again, we can write down the Raj code by the exact same method. So row 1, we have 1, 2, 3, 4 boxes. Row 2, how many? 5. 2, 1, 1, 1. So we write down the Raj code. So let's just compare with the Raj code defined by earlier. So we start with the first position, which is 3. What is the longest increasing subsequence that starts with 3? I think it's 3, 5, 6, right? And then how many letters did we skip? We skipped 7, 2, 1, 4. 4 letters. 4. Okay, if you don't believe me, you can compute a couple more. You get exact same sequence. And that tells you the leading monomial for the top Grothendieck. And what is the Castor-Novel-Mumford regularity for this permutation? You just count how many snowflakes are there. So the regularity is 1, 2, 3, 4. All right? Okay, and then we prove this result. So far we have obtained a unified rule for computing leading monomial for both top Lascoux and top Grothendieck using this very diagrammatic construction. And the last page is an advertisement. So first, Tianyi has a very, very recent preprint. He showed that top Lascoux polynomials are just Schubert polynomials after reversal. You can stare at the monomials, and they are complement by I think by 3, and you turn them around. And the second advertisement, Nick Mayers along with Felix Hutchinson, they're both from NC State. They're working on generalizing this Raj code to more general diagram, like beyond the key diagram and Roth diagram, and they're looking for collaborators. So if you're interested in this topic, I encourage you to talk to Nick. Nick, can you stand up? Right, that's Nick, my office mate. All right, okay, so we have some interesting problem we can work on. And thank you, and I'm on the job market. Very important.